Sometimes when I do these videos, I'm at school in the classroom. Today, I'm at my cottage in Muskoka. No, my villa in Mexico. No, Monaco. Monaco. Yeah. You like the blue? I picked the blue. Anyhow, today we're talking about quantum numbers and turning that into bonding. How do we understand bonding? How do we turn our mathematical model into something that's usable for very real things? Molecules, atoms. Atoms forming bonds to make molecules. That's our focus for today. So let's take a quick little review of quantum numbers, and then we'll turn this into something we can use for bonding. So we've got 4 quantum numbers. First one is the value of n, principal quantum number. And it can be any counting number, 1, 2, 3, 4, and so on. And we use that to represent the overall energy level for the electron. And then we have our value of L, which is the secondary quantum number, or it's got a couple of other names. But we've been talking about using this to determine the shape of our orbital. So we'll sometimes, instead of using values of numbers, 0, 1, 2, 3, we'll use letter values. So our L0 orbital is sometimes called an S orbital. L equals 1, P orbital, and so on. But let's just stick with the numbers for the time being. Then we have our M sub L, magnetic quantum number. That tells us the orientation. The more possible values there are, the more possible orientations there are. And then finally, we have the spin number. The spin number is either plus 1/2 or minus 1/2. And the first 3 recognize the electron as having wave-like particles. And the fourth number, the spin number, recognizes the electron is a particle that has a spin. So let's take a specific example. If n were equal to 3, so possible quantum numbers for an electron in the third energy level, big long question, we would say n equals 3. L can be 0, 1, or 2, and then M sub L can be anything from -2 up to +2, and of course spin, always the same, can either be plus 1/2 or minus 1/2. But what does that mean, and how do we turn that into information on bonding? So taking a look at it in a little bit more detail. N is the energy level, as I said, L, shape of the orbital, M sub L, number of orientations. And this is key, that the number of orientations, more orientations means more orbitals, more possible orbitals of that sub-energy level. And then finally the spin. We've already talked about that. So if each electron has to have a unique set of numbers, and I need to have, say, lots of electrons possible in my third energy level, then these quantum numbers have to kind of, I need to be able to expand them a little bit. So let's try that. Let's take this down, take this n equals 3 example, and break it down in much more detail. Taking back n equals 3 again. Well, what does that mean? If I look at each value of L individually, leave some space so that I can look at what M sub L means for each value of L. In other words, if L equals 0, what does it mean for M sub L? If L equals 1, what does that mean? In other words, if I look at each value of L in turn, then I have values of M sub L being -1, 0, 1, and -2, -1, 0, 1, 2. And then finally, bringing my spins into the equation, I have spins of plus 1/2 or minus 1/2 all the way across. And if I start looking at all the different possible combinations to have a unique unique set of quantum numbers, I actually now have much more electrons. However, more importantly than that is, how do I turn that into something that I can use to represent an atom with electrons that is capable of bonding? We're going to use a box. So in the first one, with L equals 0 and M sub L equals 0, only one orientation, only one box. If L is equal to 1, then I can have -1, 0, or 1. 3 orientations, 3 boxes. And finally, with 5 orientations, 5 boxes. What about electrons? Well, electrons, sometimes I represent them as dots. This time I'm going to represent them as arrows. I'm going to have an arrow pointing up to be a spin of plus 1/2, and an arrow pointing down to be a spin of minus 1/2. Will I know the spin? No. Does it matter? No. So I'm now just representing electrons, not necessarily making a really accurate picture of them, but an accurate enough picture that I can talk about bonding. So my atom might look like this, where I've got 2 electrons in the s orbital, and then I've got 2, 3, 4 electrons in the p orbital, or L equals 1. Okay, how do we turn that into bonding? Well, we know that with a covalent bond, one atom brings an electron, the other atom brings an electron. Those electrons pair up and form a pair of electrons. So how would we work that out over here? Well, this could look something like this. So if I take the atom that I just had, my boxes with electrons or arrows in them, and I have two single electrons in that atom. So I could line this up with two separate atoms that also have a single electron. And then I could say that those orbitals are going to overlap, one from the first atom, one from the other atom, one from the first atom, the other from the third atom. And I could say I now have two bonds. Or I could have one atom bringing two electrons and another atom of the same type or even a different type bringing two electrons. And now I could have a double bond. In each case, I've got single electrons forming pairs of electrons. There's going to be much more detail to it than that, but for right now, this is how we're going to represent our electrons. This is how we're going to do it for atoms. This is how we'll do it for molecules. We'll figure out in class, how do we figure out how many electrons go where do they go, where do I put them spin up, spin down, all those other questions that you might be having right now, we'll take care of that in class. But right now, we need to see the picture of what we're going to use to represent electrons as they form bonds to make molecules. Talk to you in class.